Okay, let's get started. We're going to be doing experiment 16, which covers colligative properties. And what are colligative properties? These are properties of a solution that depend only on the number of solute particles in solution, not the type or nature of it. So, an example of a colligative property would be like vapor pressure lowering. We'll talk about when we what that means is that salt water has a lower vapor pressure at the same temperature as fresh water. There's also boiling point elevation, which would be like adding radiator fluid to your radiator so that the water there doesn't boil at 100 degrees Celsius. It boils much higher. And also melting point depression. So if you're ever on the East Coast and in a place that has a lot of snow on the roads or ice on the roads, what they do is they add ice and salt on the roads and it melts the ice. What it's done is that it's depressed your melting point so that it no longer melts or freezes at 0 degrees Celsius, but at a lower temperature than that. So this lab today is going to be the melting point depression of naphthalene. So what we do is we have the melting point depression of naphthalene. Okay, so let's take a look and see how that works. Before we talk about the naphthalene in particular, the two equations that we'll be using in order to quantify this is one, molality, and it's abbreviated with a lowercase m, is equal to moles of solute over kilograms of solvent. Now notice it's not of solution, but it's of solvent. The other equation is that the difference in our freezing point, okay, is equal to the temperature of the freezing point, and this will be of my pure solvent, minus the freezing point of my solution. Okay, we also know that this change in my freezing point is going to be equal to a negative I K sub F for freezing times the molality. Alright, so these are the two equations that we're going to be using. Okay, so let's go through and talk about the different parts of these equations before we talk about the experiment. So let's talk about molality, okay? And then IKF. All right, so molality is a concentration unit. Okay, and so basically moles of solute, you know how to get that. And the reason that we use it is that with moles of solute and kilograms of solvent, there's no temperature dependence. Is this important? Volume can change with temperature, even if we are talking about liquids or even solids. So there is some slight modification in terms of volume when the temperature changes. And here, the masses and the moles don't change whatsoever. So the nice part about molality is that regardless of the temperature, it will be exactly the same. Will concentrations that involve volume change much? And the answer is no. But depending upon the level of precision that we need, and for us, our level of precision isn't high enough to detect the differences. If you need extra high precision, then you'll want to definitely mention the temperature. Okay, so this is a new type of concentration unit that you're encountering. Now the change in freezing point, the reason it's a negative, this is my freezing point, is that the freezing point of my solution is always less than the freezing point of my pure solvent. So when I subtract, it will be a negative number. And that's why we have to take into account the negative there. Okay? So, that's why we have the negative. I call the Van Hoff factor. Okay? So let's go through what that means. When you look at something like 1 molar, let's just do glucose. When this dissolves in water, suppose I have a liter here of solution. What you find is I will have 1 mole of C6H12O6. What the Van Hoff factor tells me is that for every 1 mole of solute, I have 1 mole of particles floating in a liter of solution. What happens if I take instead 1 molar sodium chloride solution? Now I have sodium and I have my chloride solution. So if you look at the number of particles, I have 1 mole of sodium ion and 1 mole of chloride ion, which means I have 2 moles of particles. So I is going to be equal to 2. In other words, it will have twice the effect on my solution properties than the 1 molar glucose. Okay, finally, K, it should be a lowercase k. Kf is my molar freezing point. Depression factor. Okay, so for naphthalene, it's 6.94 degrees Celsius per molality. So in other words, we know that for every 1 molality change, you're going to drop your freezing point by 6.94 degrees Celsius. This is substance dependent, or solvent. So we will have different values for different solvents. Okay, and you can check your lab packet, okay, for the various values. So let's go through and then talk about the lab. So what we're going to do in the lab is given our freezing point depression, delta TF, okay, and we can, and what else do we need? And basically sample mass of your unknown, and solvent. We do need our solvent mass. We can determine the molar mass of a non-volatile. Means it doesn't go into the gas phase very easily, right? Of a non-volatile unknown compound. And that is what we're going to do. What we're going to do is we're going to get delta TF. We'll get the masses of these, and then we're going to determine the molar mass of our unknown. Okay, so let's see how we're going to do this. So we have this very heavy glass tube called an ignition tube. Okay, and basically you're going to put it into a large beaker with water. You're going to have your thermometer. Okay, and you're going to have a little stir bar. Okay, and so you're going to mix your solid. Here's your cork. Okay, and what you're going to do is you're going to put your sample in here. So the first thing we're going to do is we're going to put in 15.102 grams of naphthalene. Okay, so how do we weigh it? Use a large weigh boat, weigh the boat, put in your sample, reweigh with sample, after we put it in here, the difference is going to be the mass of my naphthalene. Okay? So once we get the naphthalene in here, we're going to heat over my hot plate the water, and you're going to just keep heating it until this is completely melted. Okay? So it'll be over 80 degrees, usually around 86 or so degrees or so. You'll see this is completely melted, and we'll use this stir rod to make sure everything's been okay. Once your naphthalene is completely melted, then what you're going to do is you're going to take the ignition tube out. You're basically going to dry up your tube. You'll put it in a jar with some paper towels here. The reason you're doing this is just to prevent air currents from affecting the rate that your naphthalene is going to solidify. And you're going to measure your temperature every 30 seconds. Okay, until it's completely solid. Usually I have you guys stop around 60 degrees Celsius. Okay, and you do this for naphthalene, and then once it's done, you set it again, so you know how much naphthalene you have. You have now, instead of just having naphthalene, remember the amount was 15.102 grams, and you're going to add 2.068 grams, okay, of your sample. Okay, when you do that, you're going to reheat it. So you'll do this again. You'll reheat the second run. You reheat till it's all melted. Make sure you mix it because you're trying to make sure you have a mixture. So usually what I do is, like, when it's all solid, I say go ahead, add your unknown to the solid, and as you're melting it, you're going to use a rod and mix it, and that'll help speed it up. Make sure you reheat it so you mix it so it's all basically in solution. Reheat once it's all melted, then go ahead and do this again for your second run. Okay. So once you do that, you're going to have a graph, and it's going to look like this. This is your temperature in degrees Celsius, and this is your time in seconds. Okay? And let's say the first one starts at 86 degrees. Okay? So we'll say both of them start at 86 degrees. So the first one, over time, begins to melt, but once we hit about 80 degrees, it plateaus. Okay, what's happening here? Well, what's happening is everything that is a liquid is now becoming a solid. So remember when we were talking about phase changes, this is where all my liquid becomes solid. Okay, now this, if you're mixing well as it's cooling down, you won't see a significant drop here, or it'll be very minor. This is if it's super cooled. What that means is that I have a liquid, and if it goes below my melting point, it's an unstable type of situation. And then once it starts becoming a solid, all the additional heat gets released. That's why it goes up, and now it's going to be here, and the remaining liquid becomes a solid. Okay, and it gets very hard to mix it when you have a solid, but that's what happens. Okay, and then finally, it takes quite a bit of time, it'll start to cool down. And we'll stop when you hit about 60 degrees. Okay? So this is just pure solving. It's my naphthalene. Okay? Okay? Now when we do our mixture, I'm going to erase this so I can write it. When we do our mixture, we don't, to have it all become liquid, most of the time people pull out before it hits something like as high as 86. It might be somewhere lower than that. Okay? And what happens here, okay, is that It'll cool. Okay. And you get a similar type of profile for your solution. Okay. Not always pretty because this happens so rapidly before it starts cooling down. It's hard to see the plateau. And this is going to be your solution. Okay. So it's my naphthalene with my unknown. Okay. And what you're going to do once you make your graphs, you're going to find a ruler. And in this case, I'll just have to draw it. Where it plateaus right here. If you draw your line back to where it plateaus, you're going to find that this is T, my freezing point of my solvent. Okay, and this should be about 80.3 degrees Celsius. Okay, if you do the same thing, so let's say this is my plateau right here. Okay, this is the freezing point of my solution. Okay, and when you read it, it's about, say, 74.2 degrees Celsius. Okay, let me give you a darker green so you can see that. 74.2 degrees Celsius. Okay, so now we have our two freezing points. And the difference, this difference here, is delta TF. Okay, so 80.3. I'll write it down. So this is what your graph should look like. So TF of my solvent, 80.3 degrees Celsius. TF of my solution is going to be 74.2 degrees Celsius. Okay, so we know that the mass of my naphthalene was 15.102 grams. Okay, we know that the mass of my unknown is equal to 2.068 grams. Let me just tell you that the unknown is the molecular non-volatile compound. Why is this important? This means that my Van 't Hoff factor I is equal to 1. Because remember, if it's molecular, even if it's soluble, it's not going to come apart into any components. Okay? So we know that I is 1. All right? And we also know that for naphthalene, our molar depression point factor for naphthalene is going to be equal to 6.94 degrees Celsius per molality. Okay? And from all of this, this is what you need to get. You need to determine the molar mass of the unknown, and 2, given the molar mass of the unknown, is 156.27 grams per mole. You're going to determine the percent error. Okay, so that's what you have to do for experiment 16. Okay, and what we'll do is, let me give you one example. Okay, so let's do an example. Suppose we have an example where the amount of naphthalene that you used was 14.986 grams. Let me just headline that example. Okay, and the sample was 2.150 grams. We know Kf is equal to 6.94 degrees Celsius per molality. We know I is equal to 1. And what I want to do is, when you measure the temperatures, the freezing point of my solvent, the naphthalene, is 80.3 degrees Celsius. The freezing point of my solution is equal to 74.7 degrees Celsius. From here, we're going to determine the molar mass of the sample. Okay, so let's go ahead and work with this data. We know that delta T, my freezing point, can be equal to 74.7 degrees Celsius minus 80.3 degrees Celsius. Okay, so delta TF is going to be equal to negative 5.6 degrees Celsius. Okay, taking care of that. I is 1. So let's go through this. We know delta TF is equal to minus I KF M. So we can find our molality. M is equal to minus 1 times 6.94 degrees Celsius per molality divided by delta TF, a negative 5.6 degrees Celsius. Okay. Oh, I have that inverted. Sorry. And it's the other way around. Delta TF minus I KF. Okay. So I have that inverted. A minus 5.6 degrees Celsius divided by 1. 6.94 degrees Celsius over molality. And if I do this, I get something like 0.807. And molality, remember, is grams per, or moles of solute over kilograms of solvent. Okay, so now that we know our molality, we know that molality is equal to moles of solute over kilograms of solvent. Okay, so let me just separate the two. This is the first part of my calculations. The second part is getting our moles of solute. So the moles of solute would be equal to the molality times the kilograms of solvent. So we're going to have to convert grams to kilograms. And that's going to be equal to 0.807 moles per kilogram. Okay, and be aware that's two significant figures, but I'm not done with my calculations, okay? Times 0.014986 kilograms, okay? Which means that my molality is equal to 0.0121 moles. And this is my moles of solute. Okay, and we'll stop and let me change batteries, and then we'll find out what this molar mass will be. Okay, and let's just finish the last set of calculations here. So I have the moles of solute, and I have the sample. Okay, so let me just write down the moles of solute, then we can finish off our calculations. Okay. So to finish off our calculations then, molar mass is equal to moles over mass, right? No, not silly. Mass over moles, which is 2.150 grams divided by 0.0121 moles. Okay, which means that my molar mass is, I get something like 178 grams per mole. Okay, so that's exactly how you're going to do with the set of data I gave you earlier from your experiment. That's exactly how you're going to go through your calculations to get the molar mass. Now suppose that the molar mass is 177 grams per mole. This is your given. And the percent error, remember, is going to be equal to the 177 minus your experimental 178 divided by the 177 times 100%. Okay, and so we get 0.6% error. Okay, so that's what I want you to do, exactly those types of calculations, but I gave you your own set of data to work with and your own unknown. You're going to calculate the molar mass of your unknown, and you're going to calculate the percent error, and then you're going to finish the application of principles, and that would be for experiment 16. Okay, good luck.